Recording.
Okay, welcome everyone to this session of the seminar on PDs and applied mathematics. Today we have the honor and pleasure to have with us Professor Rafael Granero from the University of Cantabria in Spain. He got his PhD under supervision of Diego Córdoba at the Institute of Mathematical Sciences in Madrid, and after that he became Arthur J. Krenner Assistant Professor at the University of California in Davis. Then, during the years 2016 and 17, he was a Million researcher at Lyon University in France, related to a Center of Excellence in Mathematics. And since 2017, he has been professor at the University of Cantabria. We can also mention that he has been awarded with the Vicente Caser Research Prize for the Royal Spanish Mathematical Society and the Antonio Valle Research Prize by the Spanish Society of Applied Mathematics. So thank you very much, Rafa, for having accepted our invitation to give this talk, and all yours.
Thank you. Thank you for the invitation. Okay, I'm going to talk about a fluid-solid interaction problem. So let me try to start with the setting. Oh, why is this thing not moving? Okay. Okay. So I'm going to. By the way, this is a joint work with Diego Alonso. So far we are going to consider a two-dimensional fluid. So I don't know whether you see my mouse. Can you see it? Okay, so this blue region that's the two-dimensional region occupied by the fluid. So and the solid blue line is the an elastic membrane. Okay, and on top we assume that there is vacuum. Okay. Um, so basically, if we consider that we have a Hill cell or a porous media for the fluid, then the full system of equation is described by this. So here, although this is a 3, it should be a 2. So here we have the Darcy's law. Mu and kappa are constants, and rho and g are also constant. So mu is related to the viscosity of the fluid. Kappa is the permeability of the porous medium, or is related to the width of the Hill cell. Rho is the density of the fluid. Capital G is the gravity. Oh, this E3 should be another 2. And this he is just, so imagine is 1. This guy is related to whether we are in the Rayleigh-Taylor stable or the Rayleigh-Taylor unstable regime. Okay, so whether gravity is pointing downward or upward, if you think it doesn't really matter. So think it's just 1. Then because of the fluid being incompressible, then the divergence of the velocity field should be 0. So U is the velocity of the fluid, and P is the pressure of the fluid. And then, so these two equations are satisfied in the bulk, in the blue bulk of the fluid, and then in the elastic, so the elastic membrane is assumed to be a graph. Let's say is the graph of the function h, and then the elastic membrane satisfies this evolution equation right here. So it's just transported by the fluid. And then because we have a graph, we are assuming that the parameterization is given by the graph. Then we only care about the normal velocity of the normal component of the velocity. Okay, and then so here there will be another boundary, and then we have U2 will be 0. So that means that the boundary is a wall, it's a solid wall, it's an impervious boundary. Okay, and then these are the laws for the fluid, and then this is the law, let's say, for the solid, and this is the law that actually communicates both things. So the pressure of the fluid on the gamma, on capital gamma, satisfies this boundary condition. Okay, so capital E is just this elastic operator. So H is the mean curvature, kappa, capital K is the Gauss curvature, and then delta sub gamma is the Laplace-Beltrami operator. But so imagine that this guy is just a B-Laplacian. It's a nonlinear B-Laplacian if you like. Okay. So why the bilaplation? Because so basically the curvature has two derivative, and then this Laplace-Beltrami is hitting the curvature. So imagine that this is only just four derivative of h, okay, in space. And then this term right here, this capital D, is related to some sort of viscoelastic diffusion. Okay, so this is just a pure elastic motion, and then it's assumed that the elastic solid also has certain damping mechanism. And the damping mechanism is modeled by the Laplacian um, of the time derivative of h. Uh, okay, so imagine, so this is just h txx. Okay, so it's basically one derivative in time, two derivative in space. So okay, you already see that it's a kind of a high order system of PDEs. There are four derivatives right here, three derivatives right here. So it's certainly high order, and it's a free boundary problem because the solid H, so the solid is assumed to be described by the graph of the function H, but the function H is itself an unknown of the problem. So here we have a number of unknowns. So you have U1, U2, the two components of the velocity, pressure, that's a third unknown, and then H, that's the fourth unknown. Okay. Um, so okay. Then so remember I call that thing the full system. Okay, so let me try to do a spoiler of my talk. I'm going to focus on so the goal will be to find asymptotic models of the full system that are appropriate in certain regimes. So here let me try to clarify what I mean. So this is a picture of this coastal engineering journal. So basically, there was an earthquake, and then a tsunami goes towards the coast in Japan. Okay, and then these are the difference. Of course, the motion of the way of the water is described by, let's say that it's described by incompressible Euler. Okay, let's assume that. So the conservation of momentum is the same in the whole water. But the thing is, because of the bathymetry and different other physical parameters, if you want, or physical constraint or setting. So basically, the same conservation of momentum have has very different translation into, let's say, wave motion. Okay, so basically, in this particular part of the coast of Japan, the surface of the water behaves like this, while in this other or here in this other region of the coast of Japan, the surface wave, the surface of the water behaves very differently. So here you see rapid oscillation. Here you just see a single peak. So this is what I mean by different physical regimes. Okay, so the full system will be the same, and then we want to focus on two of these particular regimes. Okay. So let's say we want to, so and roughly the idea is that we are going to capture a simple simplified equation that we are going to find and study simplified equation that accurately capture two of these pictures. Okay, so we say, okay, we cannot consider the full system, or maybe we can, but we don't do it here. Okay. And then we are going to focus in just two particular setting akin to two of these pictures. And then, so the particular setting that we are going to consider is whether let's say this is the sometimes called the weakly nonlinear small slope regime. Um, so here, capital H will be the typical height of the solid. Okay, so will be, let's say that this is the equilibrium, so it will be this number right here. Okay, and then capital L will be the typical wavelength. Okay, and then we will assume that this is a dimensionless quantity, and we are going to assume that this sigma is small. Okay, and we are going to focus just instead of the full system that can fully describe every situation, we are going to focus just on the situation when sigma is small, and then we want to obtain new equation that are simpler than the full system, um, probably with a smaller number of unknowns, and that is accurate to describe the full dynamics. Always that we assume that sigma is small. If sigma is not small, then our model probably cannot describe the dynamics of the full system. But if sigma is small, our model will be able to be as accurate as needed, and we can handle it instead of the full system. And then the second situation we are going to consider is when this delta is small. Delta is again is a dimensionless quantity. This little d will be the depth, typical depth, and then capital L is again the typical wavelength. So basically, sometimes this is called amplitude over nonlinearity parameter or something like this in the water wave community. And this guy right here, delta being small means that the system is in what is called sometimes in the water wave community as the shallow water regime. Okay, so basically, and let me try to skip this part here. So let me very briefly state what we do. So we consider Taylor's expansion, if you like, power series expansion on the parameter sigma, and kind of the same as the multiple scale method that the previous speaker was talking about. And then we will get similar iterative linear problems. They are they are not parabolic. They are elliptic for the bulk of the fluid, for the velocity and the pressure. And then basically because they are linear, they can be solved recursively. And then we plug what we find explicitly, because everything is linear, into the equation for little h. And after some algebraic manipulation, everything can be described. So the full system is can be described by this equation right here, which is a single equation for h, and then up to an error of order sigma squared. Okay, so this model fully captures the complete problem up to an error of order sigma squared. So, and so this problem is so this is a single PDE. Here, when we do this, so there is something we win, and the first thing we win is that instead of having four unknowns, and instead of having two-dimensional elliptic operators, we have just a single unknown, little h, and then a single one-dimensional nonlinear PDE. So this is what we get. Say the main advantage. So instead of considering the free boundary problem, we just have to consider this guy right here. And then the price to pay is that Okay, every time we solve the elliptic operator, so we get this lambda. Lambda is a differential operator. Is the square root of the minus Laplacian. So in Fourier side, this lambda is absolute value of the Fourier variable chi. Okay, so and the hyperbolic tangent of lambda means the Fourier operator given by the multiplier hyperbolic tangent of absolute value of chi on the Fourier side. So basically, everything can be reduced. So the full system can be described by this single nonlinear and non-local, because every time we have these Fourier multiplier operators, we have some non-locality present in the problem, and up to an order, up to an error of order sigma squared. Okay, so we reduce so we change from four unknowns to just one unknown. Instead of a free boundary problem, instead of a nonlinear free boundary problem, we have a nonlinear and non-local single PDE. Okay. Now, let me although this PDE seems kind of weird, let me try to how to say explain every term by itself. So first, so it is kind of a weird PDE in the sense that so the time derivative. So this is an evolutionary PDE for h, but we see that the time derivative appears three times. So it appears, of course, on the left-hand side of the equality. That will be the best friend we have, right? But then, if oh, by the way, lambda and theta are dimensionless quantities. So imagine here everything is a one, okay? So imagine every parameter here is a one. Um, so so of course we want something like time derivative of h equal to something, but the problem is that on the right hand side there are also time derivative of h. So first we have to somehow invert this operator. Otherwise we don't have a how to say a bona fide evolutionary problem for h. Okay. And second, the problem. Okay. So if this guy wasn't here, if this last line wasn't here, then this guy is a spatial operator, is an elliptic operator acting on the time derivative. It can be solved on the Fourier side. It's a third order operator. There are two derivatives here, but there is a lambda here. So basically, this is like lambda cube. Hyperbolic tangent is bounded by one. So basically, every time we see an hyperbolic tangent, we can intuitively think it's a one. It's not, and there is some computation we have to do to rigorously estimate everything. But imagine there is a one. The main contribution is whether this guy is a one. That will be the high frequencies. So basically, this guy right here is an elliptic operator of order 3. One derivative coming from the lambda, two derivative coming from the two derivatives with the minus, and so this guy on the Fourier side will be chi to power cube, hyperbolic tangent of absolute value of chi. So basically, this is a always positive Fourier multiplier. We can solve it. But the fact that we have, so on the right hand side, every time we have a time derivative, it has a friend that goes with him, and it's a nonlinear contribution, right? Because the friend is h, and in fact, if we just count the number of derivatives, it seems that, so let's say that this guy right here, which is the local term, so there is a term on the right hand side which is like it seems that is of order 4. Why 4? Because this, when we distribute this time derivative, this space derivative, so we will get a term like 4 derivative in x hitting a time derivative of h. So it seems that the main contribution for the time derivative of h is in fact a fourth order operator in space. Um, and here is the same, right? Because so we have lambda hyperbolic tangent, two derivatives. So basically we have like lambda squared, two derivatives. But this is again four derivative of h. Okay? So so basically it seems that on the right hand side there is a four order differential operator hitting the time derivative of h. Uh, So a fourth order nonlinear, in fact, even nonlinear operator hitting time derivative of h. So far it seems that we are hopeless, but the main how to say observation here we have to make is that in fact lambda squared is not two derivatives. It's in fact minus two derivatives. So these two guys together on the right hand side they both together group in a commutator term that in fact is a third order differential operator, nonlinear differential operator for dth. And then, so basically it's of the same order as the left hand side. So basically, when we group this, all these guys in red, in the red cloud, um, so basically we have this nonlinear third order elliptic operator. Again, as it seems is a fourth order elliptic operator, it is not because this nonlinear term is in fact a commutator. Okay? If you compute this guy carefully, the fourth derivatives disappear one with the other. And then the guys that survive are kind of one derivative hitting h, three derivative hitting ht. Okay? Of course, it's not as simple as that because the non-local character of this commutator. Okay, so it's not just a commutator of local derivatives if you want. It's a non-local term. This guy is non-local, so uh, is non-linear and non-local third order operator. Okay, then what about the space? So in space, it seems that the higher order derivatives are these guys in blue. That will be a sixth order. If we just consider this guy right here, it looks like a sixth order kind of Purus medium equation, parabolic Purus medium in the sense. I mean, however, this guy right here again present the same commutator structure. There is one lambda here, two lambda here, four derivative here. So again, it has this six order derivative hitting h, so to speak, and then the change of sign because the difference between lambda squared and two derivatives. And so again, this guy right here, it has a commutator structure, and this guy right here becomes a fifth order nonlinear and non-local differential operator, which again group with the order of this linear contribution. So, and then of course the same thing happens with the, so when we group this guy, so basically the right hand side is fifth order, and then the same thing happen with the term due to gravity. Here, the linear term, when we group this guy right here with the blue cloud, basically we have a nonlinear and non-local first order differential operator. Okay. So basically, so far what we have here is a third order nonlinear and non-local elliptic operator hitting ht. And then on the right hand side, the main contribution is a fifth order, again, nonlinear and non-local differential operator hitting h. So basically, so what we expect, so to speak, in a sense, I don't know, roughly speaking, and the way I think on this equation is like is kind of we expect a parabolic behavior for this guy. Okay, so we expect a parabolic behavior for this guy because basically the idea is that we can invert this uh, third order elliptic operator. So let's say we subtract three derivatives to the h, and then basically we have kind of a heat equation, a nonlinear heat equation for h. Okay, so basically, if I will have to classify this equation, I would say it's a second order um, um, parabolic PD, so to speak. It's not. I mean, this is intuition. Okay. So basically, so once we have derived the equation, once I tried my best to how to say, create some intuition about these different terms. Let me present the well-Posner theory that we have. So basically, let me first focus on the case with lambda equal to zero. So if lambda is equal to zero, there is no high. So this guy right here disappears. Okay. So there is no this fifth order contribution. Okay. It doesn't matter, and we have a theorem for lambda which is not zero. Okay, let me do this theorem first. I will try to focus. I will try to sketch, so to speak, the proof, and then I will present the statement for lambda different than zero. Okay, so basically, what we are able to say is that if I will present the space A1 in a minute. But basically, in a space of which is smaller than C1, okay. Um, so if the initial data has one classical derivative and is small enough in this space that I will present in a minute, then there is a solution, a mild solution, and by mild solution, I mean solution in the integral form where this capital L, calligraphic L, is the nonlinear elliptic operator we have to solve. So basically, we are able to prove the local solution in the of a local mild solution. Okay, for small data in this space A1. Then the space A1 is the space where the first derivative on the Fourier side is so the norm of f in A1 is the little one norm of absolute value of k f hat k. Okay, so it's the derivative must be absolutely summable, if you like, the Fourier series. I mean, okay. So and then if besides being A1, the initial so small in A1 is lies in A3, although you don't need to be small in A3. Okay, you only need to be small in A1. A3 is a subspace contained in A1. So then the solution is global and it decays to zero. Okay. So and when in A1 you have a classical solution. In the case lambda equal to zero. Okay. So basically, the equation I present, so it has a nonlinear right-hand side that only depends on space, which is this guy right here. Remember that lambda is equal to zero. I'm going to present the case lambda equal to zero. And then the left-hand side, it has a nonlinear and non-local elliptic operator hitting ht. And this is the non-local and nonlinear elliptic operator. This g0 is absolute value on the Fourier side is this lambda hyperbolic tangent of lambda, okay, that I wrote before. Um, okay, so basically, this is the how to say a compact way of writing the equation. Okay, so then the idea we are going to do is the following. So first, I'm so let's say in order to prove the mild solution, the existence of a mild solution, so the scheme would be the following. So let's say I have a given h, let's say h bar, okay? And then I will put an h bar right here. So I'm going to solve first the elliptic operator because so I can solve L0 because it's just dividing on the Fourier side. So when I say I will solve for this elliptic operator, I mean I will do a fixed point to be able to solve the nonlinear elliptic operator. And then once I do the fixed point to solve the nonlinear elliptic operator for a given h bar, then I will consider the mapping that maps h bar into h, solving this guy right here. And then again, I will have to do a second fixed point. So in the first fixed point, I will win. And both fixed point theorems will be Banach fixed point theorems. So it's basically the contrastive mapping theorem. So what is small in the elliptic operator? The term that is going to be small in the elliptic operator is h in A1. That is the reason for the smallness in the assumption in the theorem, okay? So it's in order we can solve this elliptic operator, in order we can prove that there is a fixed point, okay? And then the second fixed point, the thing that is going to be small is the time of existence, okay? And that's how we will win. So basically, let's say we consider h bar. So every time we see here an h is data, it's not an unknown, it's h bar. Okay, every time we see here h is h bar and it's data. So basically, and this is analytic, and this is v is also data. Okay, and this is a problem that is an elliptic problem. L0 is a multiplier, but is a always is a positive multiplier, a strictly positive multiplier. Is in fact bigger than 1. And then we can divide by the Fourier multiplier. We can solve this linear elliptic problem on the Fourier side. Okay, and in this way, for fixed h bar and capital V, we can define the mapping that solves given V and little h bar solves and recovers U. Okay. And then we consider the difference between two of these, I mean, the increment of this mapping, if you like. And then we can find this estimate right here, okay? And remember, every time we see an integer is basically you take a number of derivative of the unknown, take the Fourier series of the number of derivative, and that thing must be absolutely convergent. Okay, so basically, once we have this estimate, now it's a matter of little, so h in A1 being small enough. And if h in A1 is small enough, we can apply Banach fixed point theorem, and then we will have that there is a fixed point for this mapping, but that means that we have a solution for the nonlinear elliptic operator. And also the solution will satisfy this estimate right here. Now, once we have a mapping that eats h bar and returns capital U, then we can consider the mapping that eats h bar, returns capital U, integrate in time, and then makes this guy right here. And this is a mapping that eats h bar and returns h. Okay, and then so basically now we want to do a fixed point right here, and we do the fixed point in this space in L infinity in time, A1 in space. And again, we can find this estimate right here, and if we find this estimate right here, now it's a matter of capital T being small enough. And then if capital T is small enough, we have to find a fixed point, and then, but a fixed point is a mild solution of our problem. Now, what happens if you are A1? So basically, if the initial data is also A1, A3, then because of the elliptic estimate we had before for capital U, but capital U is HT. So basically, we have that the time derivative of H is A3. So if the initial data is also A3, then the solution remains A3. That's in a sense propagation of regularity, if you like. And then we can use the linear terms to eat part of the nonlinear terms, and then basically we have that this norm right here decays for maybe even smaller than for the requirement of the solution to exist. Maybe we have to consider even smaller data in A1 in order that the solution is global. Okay, but we are not checking the particular size of the restriction we are making. Okay, so let's say it's small and that's all. And then, so basically, once we have the bound right here, this guy right here will be again h in a1 plus, so we have this guy right here. So this, if as this is small, it can be, how to say, absorbed by this contribution. And uh, and then basically every time we have a time derivative of h in a3, basically we have h in a1, h in a1 squared. So basically this is a nonlinear contribution, high order, fifth power, I don't care, of h in a1. And then if, because this is small, h in a1 is small, it can be at the end, if you like, absorbed by this guy paying with a 2 or whatever. Okay? And so we have that this quantity here decays, and we have, and that is the final, conclusion of our statement. Okay? So now, as I said, now the same theorem is true, same statement, if lambda is not equal to 0. The proof is not exactly the same, because in addition to this two fixed point scheme, we will need to do a modifier of the higher order term. We will have to do a modifier of this guy. Okay, we have to do a modifier here, and then the same two fixed point theorems. Okay, and then pass to the limit in the modifier. So it's kind of more technical, but the same result is true. Okay, same result. So now let me finish with the thin film. So what about in this case? Okay, in the shallow water or thin film regime, we call it here thin film, although shallow water is more used in the water wave community. So basically, the system that we get is this one, where mu again has so again we have a nonlinear elliptic operator hitting the time derivative of h. Here, instead of having, so the system here is local, okay, and the order of the the nonlinear elliptic operator hitting the time derivative is not 3 but 4, and before the order of the space derivative it was 5. Here is not 5 but 6. So the order of the derivative is different. The order of so the character is different. The character here is purely local. Previously it was completely non-local. So in that sense it's different. But then there are some similarities. So we have to solve a nonlinear elliptic operator in order to give a meaning to the equation. Um, and still we have a higher order, formally like a high order nonlinear, in this case local, but nonlinear PDE. But if you, so to speak, subtract the order of the elliptic operator hitting the time derivative and the order of the space operator, so again it will be like formally and intuitively this will be like a nonlinear parabolic equation of heat type. Okay, like one derivative in time, two derivative in space. So this is what I said. The theorem is oops. Okay, the theorem is not this one. In fact, this is the for the case lambda non-zero. Uh, so here, but so let me state the theorem in this case. So basically, here, if h is small in A1 and the h lies in A3, then the main solution exists, and exists globally. So it's basically the same result as before, although the equation is different. And then just very quickly the conclusion. So basically both PDEs present a double nonlinear character in the sense that both PDEs have nonlinear elliptic operator acting on the time derivative. so this is in contrast with most of the PDE that, let's say, classical PDE that appear in the literature that has time derivative equal to something. Sometimes there is an elliptic operator hitting the time derivative. For instance, in the Benjamin Bonham-Mahoney equation, there is an elliptic operator hitting the time derivative, but the elliptic operator is linear. So I'm not claiming they are the only PDEs that having this nonlinear elliptic. There are other ones. I'm aware of other cases where there are nonlinear elliptic operator hitting the time derivative, but they are, in my opinion, they are not that common. And so I think it's interesting to observe this to emphasize this point. And then in both cases, in order we can have a well-posness theorem, we need um, smallness in a space that is smaller than A1. Sorry, that is smaller than C1. The reason in the non-local case is obvious, is because of the non-local character. The singular integral operators are not well behaved in C1, but they are well behaved in A1. The reason in the elliptic operator is in the shallow water is maybe less obvious, but I think is actually also required. It's not a technical. In my opinion, it's not a technical. It's not a technical point. I don't know. Maybe you are able to prove the result without this A1, maybe in C1, but I think I cannot. And and then one of the small slope is non-local, and the shallow water is completely local. The order of the operators are different, but uh, if you formally think that the order of a space derivative on the right hand side and you subtract the order of a space derivative in the elliptic operator, they remain a heat equation, a nonlinear heat equation, in the sense that we will have a time derivative of something equal at two derivatives in a space of something else. So in that sense is what I'm saying, that there is a common similarity in terms of although the orders are different, the how to say the order in spirit of the equation is the same. And that's all. Thank you.
Okay, Rafael, thank you very much for your interesting talk. Yes. We will give the option now to the audience to ask questions or comments. So if any of you have something to ask, he or she will be very welcome. So I think that Juan, do you open the micro, Juan, or?
Uh, may I ask something?
Yes, Pavel, go ahead.
Yeah, thank you. Rafael, thank you for excellent talk. That was really interesting to see this, well, the way these operators enter. Could you please open one more time to take a look at this definition of operator lambda, how you actually
Oh,
define that?
actually, I didn't write that thing. But so lambda is the square root of the minus Laplacian. In this case, so is the on the Fourier side is absolute value of the Fourier variable t.
Yeah, so when you say it's nonlinear, it's actually you mean that the
Oh, I
differential
mean,
operator enters in nonlinear way, right?
yeah. Lambda is a completely linear operator. I'm saying that this guy. So let's say this guy, the red guys.
Uh-huh.
Uh, so again, this you have this lambda hitting this particular
No, no,
nonlinear.
no, no, no. I get it. I get it. So this guy altogether is nonlinear, right? But
Yes,
lambda
yes.
is itself, let's say,
Lambda is itself linear. Yes, yes.
it's a pseudo
Definitely.
differential but linear operator, right?
Yeah. It's pseudo differential but linear operator. Yes, yes. And this hyperbolic tangent doesn't matter. It's completely so it's just the Fourier multiplier instead of being absolute value of chi is absolute value of chi hyperbolic tangent of absolute value of chi. So imagine it's a one.
Yeah, I got it. So it's really like it's really nice that our talks fall in the same session of this seminar, right? Because it's sort of some resemblance, and I would really curious to see. Okay, so assume that we do some let's say rational linear approximation of this tangent. I'm more or less sure that you can somehow express this dt like without yeah, of course, you need to do something about nonlinearity, but still I think you can really express this dt assuming that you do some expansion of this tangent lambda, right?
I mean, yeah, certainly. I mean, and sometimes in I mean, I'm sure you are very aware of cases where from the full free boundary in certain, let's say, for long wave, whatever, and then you focus on a small absolute on a small Fourier variable, and then you do. In that case, it's a Taylor. It's not Pade, but it's a
Right,
Taylor
right, right.
the hyperbolic tangent, and that's how you get, for instance, in a spirit, if you want an equation similar to KDV or something like that. Actually, KDV.
Yeah, yeah. And well, one more question maybe. When you have this, okay, so you study these waves, which are like the motivation is given by this Japanese paper of coastal engineering, right? So basically, it's a wave hitting the waterfront, right? The coast, basically. So this singularity which emerges when you have zero depth. So well, how exactly you treat that? So like very intuitively.
Yeah, actually, in fact, yeah. So this is just for, let's say, motivation. In
Uh-huh.
fact, the full system will. So far, I think that there is not a single, uh, let's say, mathematical, fully rigorous mathematical result for the case of vanishing depth. Like when you have,
Uh-huh.
let's say,
Uh-huh.
cavitation, right? Or when you have the free boundary hitting the boundary. When you have the free boundary hitting the fixed boundary. Okay? And in fact, there are works trying to understand this problem by, for instance, Roberto Camasa has at least two papers trying to, not for the full system, but for the Saint-Venant or shallow water equation, which is completely local approximation, try to how to say to understand this situation when you have zero depth. And then David Lan is also working on that. But in fact, I think that there is no solution for the. At least I'm not aware of any paper that rigorously established the existence of solution when this H reach gamma bot.
Right.
So the full system crashes. Uh, the local so here we in our paper we didn't study that thing. So
So
we are
you
not
stay you're
so
saying you keep away from this, let's say,
yes we
singular
keep away
point.
yes definitely yes we keep away our age is away from gamma bot.
Yeah, yeah.
Other models there the it has been proved that if a solution exists when h the analog of h hit gamma bot then you will have the solution cannot be global. Although that is not
Hmm.
the sense of solution. If the solution exists, it cannot be global.
Yeah, so that was my impression as well. So there is no, let's say, definitive answer to what happens in fully in
No, no.
nonlinear case. There is some group in Moscow which is doing that, let's say, in linear or linear equation, including pseudo differential linear equations. So they do it using Maslov canonical operator. But nonlinear case, I don't think there is a good way. I totally agree with you. So it was, I was like, uh, at some point I thought that you treated that, but yeah, that then you said that you are like staying away and keep this small
Yeah,
angle
yeah.
approximation.
Here we are completely away from the bottom. Yes, I will be very interested in if you can send me the references by this group in Moscow. I will be. I'm very interested. I think it's a very interesting. I mean, the full system of any free boundary dealing with when the things hit the bottom. I think any mathematical result will be a major advance.
Yeah. That's a very difficult problem. Yeah, thank you again for very interesting talk. That was really
Thank you,
amazing.
thank you.
Yeah.
If you can send me that references, I will.
Yeah. I just need to figure out your email. Maybe I can ask Professor
Oh,
Limarco.
I will write in the. Wait.
You can
Can I
write
write?
in the chat.
Yeah, that would be the easiest way. And then you can expect an
The
email
chat
from
is
me. Like,
below, there is an icon below of the chat. Can you see that, Rafa?
No, no lo veo. Pero ¿qué te
Abajo,
abajo? Aquí.
la aplicación de Zoom.
No sé qué estoy haciendo mal. Voy a hacer una
Igual,
cosa.
igual tienes que dejar de compartir eso. ¿Ahí no lo ves ahora abajo?
Ah, sí, súper.
Sí.
Thank you.